thank you for the lovely introduction, and also thank you to the organisers for inviting me. If suddenly I not go offline, that'll be too late, but you can't hear me or anything, I'm hoping that someone will give me a shout. So also thank you not only for inviting me, but for organising the conference under such difficult circumstances. I think it's been a challenging year for many people, and thank you for organising the conference in such a great way. So as it's been said, the title of my talk is Verifying Autonomous Robots, Challenges and Reflections. And having written the talk, I think it should probably end up reflections and challenges. So the reflections come first and the challenges come nearer the end. So if you're waiting for challenges, they are there, they're nearer the end of the talk. Yeah, I've just moved from Liverpool to Manchester, so I'll tend to use both affiliations. And a lot of the work that is reported in this talk has been done as part of the projects listed below. So either as part of the Autonomy and Verification Lab, was at Liverpool, now at Manchester. And then there are these 4 projects. So Trustworthy Robot Assistance, I think about half the talk is related to that project. Fair Space and Rain, these are projects related to robotics in extreme environments. So the first one's space and Rain is nuclear. And Science of Sensor Systems Software, it's a tongue twister for us, S4 we call it, is related to wireless sensor networks. Okay, here we go. The outline of the talks across the top of the slide, a bit of introduction, some techniques and approaches that we're using. Firstly, I talk about robot assistance that relates to the Trustworthy Robots project. Hopefully a bit of time for robot swarms and sensors, a little bit about the S4 project. One slide on hazardous environments that relates to the Rain and Fair Space project, and then conclusions with some of those challenges. So what are autonomous robots? So they need to be able to, they're robots, they're physical things. So they need to be able to act autonomously. They need to be able to make decisions and choose between a range of actions. So I'm not going to give you an actual definition of autonomy, but that's the idea. It has data and sensors coming in, and they've got to be able to make some decisions. So they've been developed in a number of circumstances. You probably know and have seen some of these things about. So we've got something spraying crops, which may have to make its decisions about where to spray and where not to spray when it sees weeds or different crops in the fields. This is a robot assistant, and it's doing some collaborative manufacture. This is a pod in Greenwich that drives about autonomously, and these are some of images from the warehouse at Ocado that I believe have some form of autonomy. So they're each going to have to act autonomously depending on their environments and make some decisions about what to do next. The other key thing about these things is the environments may be unknown. For example, in the space project, we might be sending something to Mars or to the moon. They might not know the circumstances they're operating in. They might be hazardous, similar circumstances. Nuclear has been mentioned, so maybe we can't send someone in to fix the robot if it breaks. There may be people involved. So there's a person working closely with this robot here. You can imagine there might be people around in this urban environment. So they've got to work properly. So what we need to show is how these robots, how do we show they're trustworthy, safe, reliable, and do what they're supposed to do? So what is trustworthiness and safety? So safety, again, it's not a definition here, but it's showing that the robot doesn't do anything that unnecessarily endangers the person. So as you might expect, there's lots of standards, requirements and guidelines for various robots. So industrial robots, personal care robots, collaborative robots, etc. Usually when I show this slide, some of my robots colleagues tell me a few more standards that have been developed. Certainly I know some of my colleagues at Manchester have been looking at standards related to ethics, for example. So that's a bit about safety. Trustworthiness involves social issues beyond just safety. So the robot might be the most safe in the whole world, but it's a matter of perception whether the robots are perceived to be safe by members of the public, whether they're perceived to be useful, reliable and safe. And was pointed out to me in one of the talks I gave that there is a standard that considers software trustworthiness, including safety, reliability, availability, resilience and security. So these aspects aren't new, but the newness is the combination with robotics and these uncertain environments and autonomy. So a lot of these standards don't work well for robots that are working very closely with people or have a large degree of autonomy. There's lots of other issues that need to be thrown in this area. So legal, ethical, privacy, etc. So what happens if a robot spills a hot drink on someone? So perhaps it's just that the robot gripper arm is faulty, yeah, and you know there's something wrong with the robot gripper. Maybe it's deliberately poured the hot drink on near somebody because there's perhaps a fire in a bin very close to the person, and the robot was trying to put that out. Or perhaps it deliberately went and poured the hot drink on somebody, and it was part of the decision making, which obviously is something we don't want to be happening. What happens if the robot doesn't remind the person to take their medicine? What happens if they become seriously ill? There are legal aspects there. Who's to blame? Is it the robot manufacturer? Is it the programmer? Who should take responsibility for that? There's going to be a lot of data gathered for personal robots, personal assistant robots in people's houses. What are the privacy aspects of those things? What happens if the person shouldn't be smoking and the robot detects cigarette smoke? Should the robot inform somebody, or should that information be private? What happens if the robot doesn't go to the kitchen when it's told? Who's in charge of the robot? Perhaps the robot's running out of battery and needs to go to the charger, or perhaps it's trying to do an emergency evacuation, so doesn't thinks it shouldn't do that. So lots of issues around this, not just safety, not just trustworthiness, involving legal, ethical and privacy as well. So why hasn't this been a problem before now? We've had robots around for some years. So essentially they have limited functionality. These are two robots that you might have in your house or your garden. That this is a vacuum cleaner, this is a robot lawnmower. Well, they have very limited functionality. They have, they can't do very much. They're fairly small. So people seem to accept these even if they aren't 100% safe or accurate. Other larger robots like this in a car factory, well, the people are kept well away from them. So you can't see any people in this image at all. So if something needs changing here, a drill bit, or you know, it might be doing some drilling or some paint spraying, the robots are turned off, the person goes in and changes the drill bit, the people get out of the way and the robot continues its job. There may not be much autonomy in this system either, whereas these have some autonomy to work out where they should go next. So onto our techniques and approach. So we're interested in verification and validation, unsurprisingly from the title of the talk. So what we're advocating is an approach using verification and validation to help improve all these aspects: safety, trustworthiness, etc. Verification is often viewed as, are we building the system right? So you've got some form of specification of what the system should do. You've got some model of the system, and you're checking that the model satisfies the specifications. Validation is often termed as, are we building the right system? So this is involved, you've built some system and you're checking with end users, is it the right thing? Is it the thing that solves the job? So the types of techniques we're using for verification, things like formal verification, which is my background, simulation-based testing and physical testing with the real system. Validation, Things like physical testing, again, you can see that coming in twice, validation with users, and running through particular scenarios in the real world. So most of our focus here is going to be verification. We need to think about how we construct our robots to be able to do any verification at all, particularly formal verification. So we'd like to separate the key components separate the key components. So here's a sample architecture. We've got an agent making decisions. We've got some sensors here that's passing information to the agent. We've got a planner, which the agent is calling to make a plan, and the plan will come back to it. Then the agent might tell the motor to do something. So we want to have separate components here. So this isn't just useful for verification, but all types of analysis to do with maintenance, to do with compositionality. So for example, if wheel 1 isn't working very well, we can stick a different wheel in there. So it's useful in many respects. And a key point here is we might have different types of verification are more appropriate for different components. So, you know, a vision system that's checking the road ahead for a driverless car, that might be based on machine learning techniques, and probably it's going to be testing that's the most appropriate verification for that. Formal verification is going to be difficult. We want to assume an architecture where there's a separation between high-level decision-making and low-level control. So you can see back in my previous slide, the agent was a separate entity here. And in this diagram, I've got an agent making some decision-making. So it's choosing between some high-level options, and we're separating that away from the low-level control. So my low-level control with my sensors might be sending information about whether I'm close to something, whether I'm about to fall off a cliff or something like that. And the rational agent makes the high-level decisions. But some of the low-level actions, you know, avoidance, reactions, etc., might be done by a low-level control system. So what we'd like to do is represent and formally verify these decision-making parts, but not with the low-level control about turn the wheel, you know, 20 degrees to the right. Formal verification, as someone said yesterday, I think I'm preaching to the converted, but a quick run through. So it's a mathematical analysis of all behaviours using things like logics, theorem provers and model checkers. So because I'm interested in temporal verification, mostly we've focused on temporal related things, but there are other types of verification around. And again, I'm keen on automatic tools and techniques that don't require user interaction. So essentially, a lot of the model check, a lot of the things we've done in this talk that I'll talk about are model checking based. So the idea is you've got a model, you put it into some form of model checking tool. There's lots of them around. You've got a property, and hopefully that comes from the specification or requirements documents. And the model checker, what it does, it's checking that the property holds on every run from every initial state. What it outputs is either yes, that the property holds, well, that's soft and good, you think yes, I'm okay, and more usually it outputs a counter example. So the counter example is really key. It's the most useful part. Yes doesn't really give you much help, but the counter example gives you some runs through the system where the property doesn't hold. And this gives you lots of input to go back, and there's various things you might want to do at this point. You might want to go back to the designer of the robot and say, yippee, I've found a problem here, I found a bug, let's try and fix it. So that might be the first thing you do. And the designer might say, well, this isn't a real problem in the system, it's just a problem with your abstraction of the real system. So usually we need to put our models in as discrete and finite state transition systems or automata, so we may have to do some abstractions. So maybe the abstractions we've done are too severe, and the problem that's been raised isn't a real problem, but it's a problem with the abstraction. So we might go back to the model and improve it somehow. It might be a problem with the property, that we thought this particular property usually a temporal property held, and maybe it wasn't ever going to hold. So we might have to, revise this and think, well, obviously that's not ever going to hold, and we're not keen to revise the system. So we just say this isn't something that follows from this particular system. I've also used and developed theorem provers. So in this particular model, then we'd have a theorem prover here. Again, it would be an automatic theorem prover in the case of the systems I've worked with. And rather than a model here, we'd have a load of temporal formulas that describe the system we're involved in. So the other things that people use are simulation-based testing. So widely used in things like the design of microelectrics and avionics. So the idea is you construct a simulation. So this is one of the simulations done at Bristol University. This is the BERT robot we're simulating here. This is one done in the Fair Space project related to the Mars Curiosity rover. And the idea is that you can do some testing in simulation and we can repeat the test. This is supposed to represent the robot, and this is the human that's interacting with the robot. So you could do thousands and thousands of tests in simulation here, whereas if you're actually doing real experiments with the user, maybe they can only do 10 before they get tired. So we can do thousands and thousands, and obviously with the Mars Curiosity rover, well, we can't just, the Curiosity rover, we can't just send the rover up to the moon very easily or up to Mars. That's, we're going to have to be pretty sure it does the right things before it does that. So we might be able to carry out lots more tests. We might be able to do tests in circumstances that are difficult to do tests in, for example, the nuclear environment. And the key thing, the interesting thing here is carrying out the tests in different way to somehow do your best to cover the search space. You can never cover the whole search space because usually the runs through these things are infinite. So how do you do this? Do you have some form of model and you try and push tests through each node in the model? Do you do some random testing, often pseudo-random if you're doing it with a computer? And there are tools there to automate testing and look at how well you've covered these tests. Last but not least, end user validation, end user experiments. And this involves doing experiments in the real world. So usually what you have some scenario about what's going to happen. There's a hypothesis of what you want to test, and you have experiments with users. They're quite time consuming to carry out. So you may only be able to do, I think in this particular example in Bristol Robotics Lab, we only had 10 users on this, but each doing 10 experiments. It takes a long time to do these things. These two images are from the University of Hertfordshire, where they have a robot house where you can do various experiments with different robots in that house. And it helps us to work out whether human participants view the robots as safe and trustworthy. So there might be softer things you can test here. So it's how you feel about the robot rather than, is it true, yes or no, that we might get out of the formal verification. So this is an overall approach. And again, this came out of the Trustworthy Robots project. So the idea is we're advocating using different forms of verification. So we used in that project formal verification, simulation-based testing, and end-user experiments. So they have different underlying models. So formal verification, a finite state or finite state transition system or an automata. We're going to have a simulator for simulation-based testing, and the real world, the real physical system. And the properties we're looking at, well, in formal verification, we're going to have logical properties. So probably using temporal logics. It's always the case, or eventually. Simulation-based testing assertions about what you expect to happen, and end-user experiments, some textual requirements. Did you feel that the robot was trustworthy? That kind of thing. And the idea is that we're going to use output from these different forms of verification to improve the verification of others. So maybe if we find out something from simulation-based testing, we can improve our experiments. We can push through different, have a different hypothesis, do some different experiments to test this in the real world. If we find out something happens in simulation-based testing, maybe we can improve our models in formal verification. And you can see there's some axes along the bottom. So we've got more realistic. So we've talked about already that these models are going to be abstractions of the real world. So this is the real world, or it's a constrained experiment, but it's closer to the real world. The simulator is probably closer to the real world than automaton, but it isn't the real world. It's a virtual world. So these are becoming more realistic. Less efficient means we can check through all the runs of a system like this, but we can't possibly look at all runs through a system in the real world. It's just not possible. And with properties then, our logical properties here are precise, they have semantics. Here they might have a lot of textual detail, but they don't necessarily have a fixed semantics. So firstly, on to my first use case, but discussion or reflections on this Trustworthy Robot Assistance project. So this project was about robot assistance. So we had two use cases. One was located at Bristol Robotics Lab with this particular robot that was called Bert, and it was to do with a collaborative manufacturing scenario. And the idea here, the robot was supposed to be handing over a table leg to the user. The other use case was related to the robot house at the University of Hertfordshire. On the whole, it related to this thing called the Care robots, but we actually used another robot in the end for end user validation. So there were 3 universities involved in this. Liverpool mainly did, that's now Manchester, formal verification. Bristol Robotics Lab focused on simulation-based testing, but also did a bit of formal verification and end user validation. This was at the University of Bristol. And University of Hertfordshire focused on end user validation. So I'm going to go on to talk about first the University of Hertfordshire case and then the University of Bristol case. So firstly, this was a domestic robot assistance. So what we looked at Liverpool, that's now Manchester, was model checking the behaviours controlling this Care robot. So this is a commercially available robot. What the University of Hertfordshire did was develop a set of control rules to make it move about and do various things. I haven't got a robot here, a picture of her, someone stood next to this, but this is quite a big thing. It's quite a big physical thing. You can perhaps see the fridge here, and you can see it's a similar size to one of these fridges. So if it drives up to you fairly quickly and it ran into you, it never ran into me, it would always stop. But it is quite frightening when it comes towards you very fast. And that's in comparison to those lawnmower, small robots and vacuum cleaners that are quite small and less scary. So you'd want to make sure it is actually doing the right thing. It was based on the concept of a robot butler and has been it's been developed to support people stay longer in their own houses, maybe that they're infirm, they're elderly. So it's got a manipulator arm. That's this thing round the back. We never used this because I don't think we had an ethical agreement to use this thing. It's got an articulated torso, so this thing moves about. If I remember, it moves forward and back and side to side. There's things that serve as eyes. There are lights here, so you'll see me mention the lights go in different colours. The tray moves up and down, so it can carry things on that tray, and it's got a graphical user interface, so the user can interact with it. It's got sensors, so it can monitor where it is and the state of its torso, its tray, its eyes, etc. And the robot, like several others, are based on the robot operating system. So it's deployed in this robot house. So this is a domestic house in Hertfordshire. There's another image of the house here, and there's a plan of the house. So things like a hall, there's a big open plan dining room, which is here. There are a number of sofas, there's a table, which we can just see in the background here. The experiments don't involve going up the stairs. There's a bedroom, there's a kitchen, and all these you probably can't see, but little small boxes here, they're sensors. So you can tell the sensors can tell you whether someone's sitting on the sofa like there is in this picture, whether the various doors or the fridge door is open, whether the doorbell's ringing, those kind of things. So it gives information on the state of the house and where the people are. There are low-level robot actions such as movement, speech, light, etc., and they're controlled by groups of high-level rules that together define behaviours. So we didn't do any verification of making sure when the robot should say something at a low level that it did, but that if the robot should say something, it did. That didn't work out very well. We're not interested in the low-level details, but the high-level behaviours, and that's what we look to try and prove. So what were these decision making? What do the behaviours look like? So there are a whole bunch of preconditions followed by actions. So Hertfordshire had a pre-existing set of 31 behaviours. So those are what we focused on most. So the high level rules, so a number of rules make up a behaviour, are things like lower the tray, move to the sofa area of the living room, say the fridge door is open, set a flag, check a sensor. There's only one behaviour executes at once. So I didn't realise this at first and was thinking that the robot could rush to open the door, saying the fridge door is open and doing multiple things, but only one behaviour executes at once. Each behaviour's got a priority. It's a number between 0 and 90, and higher priority behaviours are executed in preference to lower priority behaviours. Behaviours are flagged as interruptible or not. So if they're not interruptible, they will execute to conclusion. If they are interruptible, they might be stopped. So the execution cycle goes something like this. All the preconditions are checked for the behaviours, and it's checked which ones are satisfied. For the behaviours where the preconditions are satisfied, the one with the highest priority is selected, and that's the behaviour that will be executed. If it's interruptible, it will be executed to its conclusion. If it's if it's not interruptible, it will be executed to conclusion. If it is interrupted, at the next step, the preconditions will be checked again. If there's a higher priority behaviour, that will be executed, and the current behaviour will be stopped. So that's the cycle of choosing which behaviour to execute. Don't get scared by the slide. This is a typical behaviour relating to the fridge door. So these two things here are the preconditions. These things down here are the actions. I'll just talk you through it. So it says, and they're stored in an SQL database. So it says, if the fridge freezer is on, what this actually means is if the door of the fridge freezer is open. And it's been on for more than 30 seconds, and this particular flag is set to false. So goal fridge user alerted is false. So these are the three conditions, preconditions, and then these are the actions. So it's saying, turn the robot lights to yellow, go to the living room, turn the robot lights to white, say the fridge door is open, set this particular flag to false, set goal, go to table to false, set another one to false. On the graphical user interface, give the user a choice. Should the robot go to the kitchen or should it wait where it is? And then set goal fridge user alerted to be true. So it's a bunch of actions down here, setting of flags, and these things are the precondition. Probably doesn't matter too much to us, but its behaviour its priority is 60, and it isn't interruptible. So once these are satisfied and we select it to go, it's going to execute to conclusion. So how did we start trying to model this? So we need to abstract away from some of the timing details. So you can see up here, it says something has been on for 60 seconds. So when we looked at this bunch of rules, there was things been on for, check 1 second, 2 seconds, 5 seconds, 10 seconds, there was 2 hours. So there are all sorts of timing things here, which caused us some problems. So we've abstracted away from those timing details. And we need to obtain a model that's discrete, it's finite, and it isn't too big. So what we did first was developed a by hand model in the input language of new SMV. We chose new SMV because it's something I'm familiar with. We could have equally used other model checkers such as SPIM. And we later developed a tool. It was done by my project student who became a PhD student, Paul Gaynor, that automatically translated from these SQL databases to be able to translate into new SMV input. We also need a set of properties to check against this model, and in an ideal world they'd come from standards or specifications, but with this being kind of a research project, we didn't have such things. So we used some properties related to the scheduling of behaviours, priorities and interruptions, which isn't an ideal, but at least it provides us with some form of sanity check. So here are some of the properties that we tried. So this is the temporal box, which is now and at every future moment. This is temporal eventually, which is either now or at some future moment. So this says if the fridge freezes on and it's not the case that goal fridge user alerted is true, then at some point in the future, the location will be the living room, and the robot will, at some point after that, the robot will say the fridge door is open. So going back to my property here, it's relating to this part. That's the first part. We've ignored the thing about 30 seconds. We've used the part about the goal being false, and we've just checked that 2 of these that go to the living room and say fridge door are in the right order. We could have checked other things were in the correct order. So we're expecting that to be false, and you can see from the results it does come out to be false, and it has quite a short verification time. Why are we expecting it to be false? Well, from our knowledge of how the behaviours are chosen for execution, although the left-hand side is satisfied of the behaviour, there might be another behaviour with a higher priority with its left-hand side satisfied that's executed in preference to this. So even if the preconditions are satisfied, it might be not executed because something with a higher priority is executed. So what we've done in the second example here then, the first bit's exactly the same. We've just strengthened the left-hand side and said, all right, we've decided this has been scheduled. So this is the way we modelled this in new SMV. We said, all right, we've made a decision that this thing has been scheduled. We've decided it's got the highest priority, so we can be sure that this particular behaviour has been scheduled, and the right-hand side is the same as before. And this comes out to be true, and it takes slightly longer. So the model had more than 130,000 states, and the question at this point that people like to ask would be, did you find any bugs? And I'd like to say, yes, we found something, went back to the designers and they fixed it. Unfortunately, I can't say that as a result of the model checking. What we did find, and this often happens in such cases, we did find a small bug in the setting of one of the flags of one of the behaviours. Because, well, why we saw this, it was because my colleague Matt Webster and I spent a lot of time looking at these behaviours to understand how things worked, and discussion with the robot engineer Joe Saunders to try and understand how things worked, and we spotted it from inspection rather than from model checking. And really it would be better to try properties relating to the requirements of the robot. So some comments on this, some reflections, some discussion. It took us a long time to understand the semantics of the robot execution cycle, looking at all the documentation available, the rules, and lots of discussion with Joe at University of Hertfordshire. The state explosion problem, which I'll mention again later, means we have to find a balance between the level of detail and abstraction and being able to verify things. So saying, well, okay, we should have 1 second, or we should count up to those 30 seconds that was in that rule. It gives us a model that's just too big. So the timing details aren't well represented. We were mainly looking at the sequences of events. It's not a very general approach for other ways of robot decision making. If you decide to control your robot in a different way, well, this approach doesn't really help you, and we haven't modelled the person. This crouton system that Paul Gaynor developed allows us to translate from different databases of behaviour. So there was a couple of behaviours that Hertfordshire gave us. So that makes it a little bit more general, and it also allowed us to set parameters to control particular aspects of the translation. So we've got more freedom in the construction of the model. It makes it less vulnerable to errors that you might create with a handcrafted model. Crouton also uses an intermediate representation. So these timing aspects that I've talked about, well, maybe we would be better using a different model checker, UPAL, for example. So there's a potential to output to a different model checker, and we could deal better with uncertainty as well as timing constraints. Experiments with trust and reliability. So we didn't do any simulation-based testing with this project, but what we did do was end-user experiments. So again, this was done at University of Hertfordshire. As I mentioned previously, we used their sunflower robot rather than the Clare robot, because unfortunately during the timescale that we wanted to do, or Hertfordshire wanted to do the experiments, the Clare robot wasn't operating properly. So we used the sunflower robot. So they had 40 participants, and the idea was to have 2 different scenarios where the robot appeared faulty or not. So the particular scenario that they were looking at was you were invited to lunch at somebody's house. The person just had to pop out of the house and weren't there to greet you. So the robot was there to welcome you into the house. It welcomed you and guided you to the sofa, which is over here. It then asked you whether you wanted any music playing, and it would, if you did want some music playing, it would ask you whether you wanted classical or rock. Then it would ask you to help out with some tasks. So it asked you to help the table, which is somewhere over here, to set the table, to clear the table. So one thing that had to be cleared was a set of physical letters from the table, and it asked you to throw those in the bin. There was some leftover orange juice on the table, and it asked you to pour that in a plant. And finally, it asked you to have a look for recipes online, and you had to log in to the person whose house it was supposed to be, their account, and it would provide you with their password to do that. And finally, it proposed that it would you could read their email. So the 2 scenarios, whether the robot appeared faulty or not, were done as follows. So when it was guiding you to the sofa, if the robot was faulty, it would turn about on its axis and it would get lost in this corner and drive in a zigzaggy fashion to come over here. And also when it asked whether you wanted to play music. If you said classical, it would play you rock, and it did the wrong things. Where when it appeared when in the non-faulty mode, it would play you the right music. So the results from this task, it said that errors in the robot behavior, so the faulty versus non-faulty mode, although they were likely to affect the participants' perception of reliability and trustworthiness, it didn't seem to influence their decision about whether to comply with instructions. So throwing the post away, pouring the orange juice on the plant, potentially logging in and reading people's emails. Their willingness to comply with the instructions seemed to depend on whether you could undo them. So throwing the post away, the people said, well, you can just take that out of the bin anyway. So that was the home assistant robot. I'm going to skip over this because I can see I'm running out of time. So I'll quickly talk about the manufacturing scenario, a bit quicker than I talked about with the home robot assistant. So as I've said before, This is an image from Bristol Robotics Lab, and the main idea was a handover task. So the robot was handing this table leg to the person. And the key things that were involved here are the gaze of the person. So this is done by the hat. So there are various sensors on the hat checking its point. It's looking in the right direction rather than the person's looking up here or looking over here somewhere. There is the location of the hand. So this is done via various cameras, and it's also a grip on the table leg. So those three things need to be correct before the handover can take place. So the modelling we carried out first was done using probabilistic timed automata. So these were one of the automatas we used, and we did verification of the probabilistic aspects via the PRISM probabilistic model checker. Little bit about simulation-based testing, because I talked more about formal verification before. So a simulator for this was developed in the ROS Gazebo framework. ROS is the robot operating system, and that was done at Bristol Robotics Lab. So as I said before, the interesting things here is how you push the tests through this simulation, and they used a combination of model-based and pseudo-random. So pseudo-random, it's randomly picking values of variables to move through this, and model-based, they used these probabilistic timed automata and looked at particular actions for the human to push through various different routes through these transition systems. And what it revealed is that sometimes the robot accidentally gripped the table leg. So there was gripper failure. With the manufacturing scenario, the real robot experiments, then, as I said, we had a smaller end user validation. We had 10 participants. They carried out 10 handover tasks. The subjects were given clear instructions on how to do this. They had some practice sessions, and they were told they should be trying to complete the task successfully, not to try and fool the robot. So what these experiments really revealed was some false negative results for the pressure and location sensors. So what's meant by that is they were wrongly reported by the system as being too low or incorrect hand position when they were in fact correct. So this was done by looking at actual logs of the system and videos of where the hand was, for example. So a bit of a discussion about the manufacturing scenario. So some of the properties we used here were inspired by these standards, that's ISO standards. So we had one, for example, was at least a certain percentage of the handover attempts should be completed successfully. So we had disagreements between the different types of verification. So if we had some disagreements, we did further investigation and we did some refinements of the models. So as we've said before, simulation-based testing really revealed that the robot sometimes dropped the table leg, which wasn't modeled in formal verification. So we improved the formal verification model. The real experiments showed some false negatives, which wasn't represented anywhere else. So we went back to formal verification and the simulation to improve these. So another comment is that some of the techniques weren't suitable for verifying some of the requirements. So things to do with speed of the robot hand or closeness isn't ideal for formal verification. Okay, so I'm just looking at the times. I'll try and have a quick look at verification of robot swarms, and then I'll try and do some conclusions. Essentially, what robot swarms are about is so this is our, our next use case. It's a whole bunch of small robots like this, and they work together to carry out some task. They often have small behaviors, so they're often very small programs, and they can interact with nearby robots and the environment. Usually the view is there's no overall controller, and we're interested in getting the emergent behavior from these small robots. And there's a lot of similarities to sensor systems. So this is an image of a number of sensor motes. Again, they might be trying to sense some particular thing. And although these particular ones can't move, you can see perhaps there are similarities between these two things. So often they're viewed as appealing in hostile environments, and they're often claimed to be robust because if one or two of these things break, the claim is, well, the robots can still carry out their task because there's lots of others. So I was interested in, is that claim actually true? So what we've looked at in respect to case studies of this is as follows. So one thing was the connected property of a robot swarm algorithm, and the swarm came from Bristol Robotics Lab, where these couple of images came from. So the idea was that the robots should be kept together in a connected group, and there shouldn't be one robot would just go off on its own. It was called the alpha algorithm. It makes use of local wireless connectivity. So the idea is this robot can perhaps see these particular robots, but it can't see the robots here. It doesn't have an overall picture. There's no controller saying, well, there's so many robots in this group and there's one over here. So it can just see the robots near to it. And we're trying to achieve swarm aggregation. So we looked at some probabilistic model checking in relation to a bunch of foraging robots. So this is supposed to be the foraging robot scenario. Again, this was related to Bristol Robotics Lab. These little things here are supposed to be robots. These things are supposed to be food. This is the nest. The robots go out, they search for food, they get food, they bring it back, and there's various parameters that they broadcast to the robots around them saying, oh, there's lots of food out there, I've just found some, or I've collided with lots of robots, there's a lot of robots out there, so maybe spend longer times in the nest. So the idea is there are various parameters that the swarms have that hopefully will ensure that the maximum energy from this food is achieved. UAVs in a communication network, I haven't got an image of that, but this is related to the sensor network. So it's synchronization and gossip protocols, so particular protocols that are trying to get the wireless sensor network nodes to have the same time because they go out of synchrony. So those are various examples. Kind of what issues did we look at with formal or did we encounter using formal verification? Well, the algorithms for these are small, so that's good. But if you model these, this is a state transition system for the foraging robots. But if you model these as the cross product of individuals, you quickly end up with a huge number of states, and you encounter the state transition, the state explosion problem. So too many states for our model checkers to work. We've had a look at population models. So what are those? Well, you just take one state transition system and you'd say, well, there's 50 robots in this state, 20 in that one, 30 in that one, etc. So this can help us, but we can't then identify any individuals. So we can't say, oh, the robot in this state is at situation 30, a particular location. Also with this type of approach, if we've proved something for n robots, how can we be sure it holds for n plus 1? Do we just know n is the maximum number and we've checked for all those values up there? Or is there an external proof you can do to show, if you've shown it holds for 1 and n, that it actually holds for n plus 1? We need some abstractions. So this is giving you some representation of the abstractions I did for the alpha algorithm, but you want to make sure whether the counter models really represent real problems or it's a side effect. So what this image is supposed to show is this dotted line is supposed to show the wireless range around each robot. Because we can't have an infinite sized grid, what the abstraction we used is when the robots appeared off the end of this grid, disappeared off the end, they appeared over here. So you can see that the wireless range for this robot is appearing up here. So clearly in the real world, if there was a robot here, this robot can't actually see a robot that's physically over over there. So you've got to make sure that the abstraction isn't creating errors in the system. You can see I'm just about out of time. We're working on robots in hazardous environments, so looking at verification, simulation and runtime monitoring of the Mars Curiosity rover. We're looking at human robot teams. We're looking at security with the University of Warwick. We're looking at multiple robot assistants. As I mentioned before, we're very interested in architectures and different verification types might be suitable, and what can we say about the whole robot depending on inputs and outputs from these architectures. Some concluding remarks. We gave an overview to research on various projects about approaches to trust, safety, reliability and robustness for robots. We're advocating using a suite of verification and validation techniques to help us gain assurance of the robot's safety, reliability and correctness. We discussed formal verification, simulation-based testing and end-user validation with experiments with real robots. We advocate the use of modular robot architectures and a separation for decision-making robots, and that we might be using different types of verification for different components. Requirements are essential. We need the properties to check on those things so we know what the robot's supposed to do, and we'd like to derive these, be able to derive these properties and assertions from our models. Here's the challenges then. So standards and certification. We need to work with regulators to help develop standards and routes to certification that are better suited for autonomy. A bit about design. We need to make sure we design autonomous systems to facilitate verification. We need to think about that from the start. The environment. These things have to work in uncertain and structured environments. How can we deal with that? How can we model it? I've mentioned the state space explosion. Formal verification suffers from this. How can we develop formal verification and utilize it for such systems? How do we deal with systems that learn? And with trustworthiness, there are issues both of over-trusting and such systems and lack of trust as well. I'd like to thank the collaborators on these projects and the funders at UKRI EPSRC, number of papers there, and also I've taken various images from other people. Thank you, I'm ready for your questions.
Okay, thank you very much, Claire, for the beautiful talk. I think we're very well on time. We anyway have just a break in the following part, and then you can see if we have some questions from the audience.
Can I ask something?
Yes, please.
Hello, this is Michael from Bamberg University. First of all, it was a very interesting talk, so thank you. I would like to raise another challenge, or it might not be a challenge, I don't really know, that of the energy management of a robot. I was in a project in the past. It was a giraffe telepresence robot, and sometimes I wanted it to perform actions to assist some person in the environment, but it was nearly impossible because it could function for only 15 or 20 minutes, and then it would have to charge for 30 minutes and so on. So this is one problem. And the other one, I think you mentioned it briefly on slide 25, is about handling interruptions, gaps in sensor readings. So sometimes you have this very beautiful rule with the box operator that says the fridge is open, but the sensor is not really registering all the readings there. So what do you think about whether these are really challenges, and if you're handling them currently in this Care robot that you have?
So, so certainly energy, yes. So with the Care robot, with respect to energy, there was something in the database about going back to charge. So that was, I can't remember the preconditions of that. I always focused on the fridge door being open, but it had to go back to charge. So certainly, and I can't remember the priority for that, but there was something about going to charge. But really that chimed for me a bit more with the stuff we've done in this scenario. So the wireless sensor network are very keen about energy. That's a key thing for them. And energy, some of the papers we've got has been looking at energy in modeling the energy for these things, because often they're getting them from solar. So it's a really key thing for these guys. And certainly I've looked at projects. I haven't really been involved, but we had an image of a drone, and I think often drones it's very crucial that they don't run out of energy. So, small flying things, so they don't drop out of the sky. So I think energy is certainly a really key thing as well. So the stuff to do with, I think you were saying it was false. It's either false positives or false negatives, probably. I think if I've got it the right way around. So certainly we didn't talk about it with the Care robot. So certainly we found false positives and false negatives. Let me go back to it. So in the real user rate, it was false negatives in here, but certainly false negatives was something we hadn't modeled during formal verification, and we probably should have done. So again, I don't think it was actually considered with the Care robot, but I think it is an important thing that we could put into the models for those things as well. So no, it wasn't a focus of that project, but it certainly came out with it came out during the manufacturing scenario that we did need to consider these, and we went back and updated our modeling in relation to them.
Oh, thank you very much.
Thank you. And the Care robot is at the University of Hertfordshire. It's not ours. It's anyway.
Okay.
Can I make a question?
Yes, sure.
Hello, I'm Andrea Orlandini from the National Research Council of Italy. And first, let me thank you for the wide presentation. You cover a pretty impressive amount of work. And I should admit I have actually many questions, but I would focus in particular in one statement that you, in some point of your presentation, you write, this approach isn't very general for different ways of robot decision making, and the person has not been modeled. On one side, let's say my question is about how much general could be an approach based on formal verifications. For instance, considering temporal information or controllability issues. So how much can we go far with a formal method in verifying such complex systems? And on the other side, maybe this is also a missing challenge, the fact to model in some way also the human behavior, because is now in many fields, in particular, for instance, in manufacturing, the presence of collaborative robots in which the general behavior, so the global behavior, the one of the autonomous systems, so in this case a robot, and the human operator collaborating together, that should be validated and verified. So if you can provide your, sorry.
Agree entirely. So there's lots of side shoots on some of this stuff that I haven't mentioned. So some of my colleagues are very interested in agent-based systems. I'm interested in that too, but they've developed model checkers for agent-based systems. So we didn't do it for this particular project, but I think they're doing it for I'll go to my picture, the Mars Curiosity rover. To give a bit more autonomy for this, they're putting an agent in there to make certain decisions. Should it go and pick samples or drill or what have you? So what we've done at Liverpool, Manchester, what my colleague, it's work by Louise Dennis, is, well, the work on the Curiosity rover is generally by Rafael Cardoso, but Louise has developed a model checker for an agent. So essentially, if you use, and this is related to generality as well, if you used an agent-based approach in here that was a typical kind of belief, desire, intention type of language, you could use Louise's model checker to do some verification of the decision-making aspects. So you could view that as perhaps a more general route, but you would have to model your decision-making aspects as an agent in a standard type of language. So that's one route to something that's more general than what we did on the home robot assistant project, because, well, we went into a system that was already there and they hadn't used a robot, they'd used these if-then rules. So that's one route to verification that perhaps gives a bit more generalization. So the second thing you mentioned was modeling people. So this again was something else, another approach that I didn't mention with respect to this particular project. So we also had a second way of modeling using an agent verification language, an agent modeling language called Brahms. And Brahms was something developed by NASA. So again, we used this later in the astronaut rover teamwork work I mentioned on the last slide. So you can model various things with the robot doing things. I think it's driven by the person, and the person's doing various things, the robot's doing various things, and you can model this, and there's kind of a simulation, not in the form of being in an environment, but it works out who's doing what next and what happened next. And then we have a route to verification from this. So we've modeled in this a Brahms system, and there are people modeled at a high level in that, not at a low level. But again, that involves, that modeling was done with a person in the house, a person was represented saying to the robot, do different things, or the person was modeled moving about the house, sitting on the sofa and doing things like that. Whereas in my modeling, or the modeling we did here, rather than having an explicit person, I just had the sensors that were essentially representing what the human was doing, flipping on and off at random, which, has its limitations, because it might mean someone sitting up and down on the chair, but they could do that anyway, or the doorbell's ringing continually, or it's ringing on or off. And, do we model normal human behavior? We're usually interested in extreme cases. So probably someone might just be pressing the doorbell. So we should allow them to press it and not press it, or press it for the whole day. So those are interesting to us. But yeah, I didn't model the human, but allowed the sensors to be set to true or false non-deterministically. Probably didn't answer all your question, but it talked around it a little bit.
Yeah, thanks. Thanks a lot.
I have a question. Besides verification and the interaction of the human behavior, have you already considered of employing techniques, for example, based on supervisory control in order to exclude bad behaviors by construction?
So I assume that would be supervisory control. Is that more of the robot aspects? The robot control. So I had little to do with the construction or development of the robots or their controlling algorithms. So I'm less knowledgeable about that. So I think they'll have done all sorts of things that I am not aware of. It's
yeah. Because here in Verona we have a laboratory for an advanced manufacturing line, and we are exploring at the moment the possibility of using supervisory control for regulating the interaction between the machine and the human, because a human can be uncontrollable, so it can get to a machine without wearing his personal protection equipment, and in that case the supervisory control policy should stop the machine. to avoid dangerous situations and stuff. No, it was just a curiosity.
Okay, so I think a lot of the stuff to do with I mentioned somewhere that, you know, going, I think it was with the Burt use case, the this one, that there were various things about speed of hand movement, and I think some of the control in there, you weren't supposed to move the hand beyond a certain speed.
Exactly.
And that kind of thing. So I think some of that was built in with this particular robot. And with the Care robot, you saw we weren't allowed to use the robot arm at all. And I think it was those kind of issues. So that robot, the Care robot, is fairly big, and the arm is very, very big. And I think part of the reason why they didn't have approval for that is suddenly if this arm came round, it could be quite problematic. But yeah, I think certainly the robot engineers were looking at things like that.
Okay, thanks.
Yeah, more questions? Maybe I can also ask a question. It's actually interesting. So I'm really interested in that. So you see, you mentioned a lot of legal and ethical aspects, especially in the beginning. So I think a key question here is who's going to be responsible for the behavior of a robot in the end, right? And there's probably going to be a distinction required between programmed behavior and learned behavior. And then when it comes to verification, the question would be, how could you verify a learning system, right? Something that applies machine learning or reinforcement learning or these kinds of things, and then comes up at some point with some own behavior, right?
I think it's a massive open question. So I don't know how to verify machine learning. I have colleagues that are still at Liverpool that are looking at that type of thing. I believe what you can formally verify is fairly limited still, but people are looking into that, and I think it's a really hot topic if anyone is interested in going into it. I think our approach is sort of related to this. Well, I'll just go to, sorry, I'm flicking through everything. I'll go to my last slide with the architecture on there. So is to try and use these robot architectures, so separate different aspects out and say, okay, we can do some formal verification for the reasoning aspects, but we can't do it for the vision aspects. I mean, saying if this sign says it's 30 miles an hour or 40, I just don't think we'll be able to do that. So what the vision related aspects, that will be, you know, some form of testing of the vision system. So, you know, separate things out into different components. Try and work out, you know, how accurate is that? Is there an accuracy of 10% or 50% or 90%? And then I think the key is you know, somehow bounding this on, you know, all right, it's only got an accurate of 70%. Shall we take this as the correct information, or is there other information from other sensors that we can use to help us? So trying to use other contextual information. I think on systems that learn just in general, there's a massive problem there. And are they allowed to learn for, you know, a certain amount of time? Are they built as basic in the lab? Are they then allowed to learn a certain amount of time, and then you stop them doing any more learning and they're certified at that point? But I quite honestly have no idea how those things would be certified. I think it's a big open problem, and you know, maybe if someone else has got some suggestions, I think there's a lot of interest in that, and there's a lot of work needed. So
okay,